Not in presentation mode, but we do see a PowerPoint. Okay,
Yes.
it's on now.
All right, great. Finally worked 3 times the charm. So today we're going to sort of talk about a little bit about our research and how we sort of combine optical and SAR data together to monitor land use land cover change. The data that we use specifically is mostly Landsat Sentinel-2 and Sentinel-1 data, although Luofan also uses a little bit ALOS Pulsar data, and we're really looking forward to the launch of NISAR, which hopefully will be launched later this year, so we can have more SAR data to use. So let me start a little bit by introducing what we do, because I know some of you, but not all of you. So we did the pre-training survey, and I went through some of the answers. I think most people are already very familiar with remote sensing and Google Earth Engine. If throughout this presentation, if you get confused or if you have questions, please feel free to stop me and ask the question, or just type the question in the chat. I'll try my best to pay attention to it. If not, I can answer it later. And also after the presentation, feel free to reach out to me if you want to learn more about what we are doing. So our project, we serve the Severe West Africa hub, and our project focusing on the ecosystem and carbon management theme. More specifically, we do land cover change mapping, we do sample-based estimates of changes, we monitor forest degradation and deforestation, and we also try to attribute the drivers of forest disturbance. And we also do some near real-time monitoring to try to focusing on the most recent forest change activities. So here are some of the things that we do, our preliminary results. So we focused on creating general land use land cover maps for the region. We also have for deforestation and forest disturbance maps for the region with drivers such as plantations, minings, different types of plantations and loggings and other stuff. The research that I do personally is the near real-time monitoring part of it. So I combine Landsat Sentinel-2 and Sentinel-1 together to increase the data density so we can detect forest change faster and sooner. So that's the part that I do. And that will be part of the presentation today. Okay, so let me introduce the team a little bit. This picture is actually taken from our last trip to Ghana. This is a very nice restaurant in Accra. So this is kind of our last dinner before we go into the wild. We took a field trip with Bash and Mary. So hello, can you mute your mic? Yes, thank you. So our team is me. I'm an assistant professor at JMU. I used to be at Boston University, and then also Curtis Woodcock, who was my PhD advisor. He's a professor at BU. We have 3 students working on a project: Kelsey Bradley, and then Caitlin Tario. Many of you might already know her. She's been involved in Sevilla for a very long time. And then there's Luofan Don. Also, his English name is River. He's joining us today. So this is the team. There's also Aditya in the middle. He's another AST member. We did the field trip together. So before we start with before we start with the sort of the main event today, I want to sort of mention a little bit background about what we do in general. So a lot of our analysis here using remote sensing data is time series analysis. So we don't look at individual images anymore. Rather, for any place that we are looking to monitor changes, we look at all of the observation ever collected by satellite images. So we look at changes over time. We look at time series data. So here I'm showing you one example. This is just one data of one pixel in one location, but this is kind of temporal data. It starts in 2002 all the way to 2008. And what we do is we try to detect if there's any changes in the pattern in the time series, and that's usually an indicator of land use and land cover change. So what we do is we developed this model called CCDC. Some of you might already heard of it. And what it does is try to fit a harmonic model to the data, and it try to look for changes. Once it finds a change, it will then insert a break in the time series, and it will start a new model, as you can see in the third plot. So at the end of the monitoring, when we go through all of the data, what we end up is these time series segments. As you can see in this example, there are two segments. And then we try to classify these segments into different land cover so that that's the full process. We detect the change, and then we try to figure out what's the land cover, a land use before the change, what's the land cover and land use after the change, and we figure out this whole thing. So for every pixel, we try to create sort of a complete land use and land cover history through time. And we've been sort of working on this model, CCDC model, for a very long time, and there's different versions of it. We've made some changes to it, sort of to adapt it to different kind of data, to different region. And also we've sort of made modification for it to work better in terms of finding the most recent changes. And that's what I do. Okay, so here is another example. This is kind of a real example. I'm showing you an example in Massachusetts. Here's a forest changed to a developed neighborhood. And as you can see, the time series is in the bottom. The model, the CCDC model, detects a change around 2001, and then we have two time series segments, one in green, one in red. The green one is before the change, the red one is after the change. You can see the signal is different, the pattern of the time series, sort of the amplitude is different. And that's how we classify it. So with training data, we can classify the segments into the land cover classes. So we know it's forest before the change, and then it's developed after the change. So that's sort of how the model works. And so what we are going to cover today is kind of two parts. I will sort of cover how we use this time series model and how we adapt it to monitor change in near real time. So what we do is I combine Landsat, Sentinel-2, and Sentinel-1 data to increase the data density, and so we can find the most recent changes in any region. Focusing on forest disturbance, forest loss, basically. And then after that, Luofan is going to cover how we map deforestation, forest degradation, and also the drivers of these changes in general using time series analysis of Landsat and Sentinel-1 data. So my part is more focusing on the most recent changes and sort of forward monitoring, and his looks at historical changes, what's been going on in the past 20 and 30 years. Okay, so my model, this is the part that I worked on for my PhD, basically. Near real-time monitoring of tropical forest disturbance. The paper is already published. If you're interested, please go to this link and read the paper. You'll learn more about how the algorithm works. But I will try to cover sort of the technical part and how to use the algorithm in your region specifically today. So the rationale of trying to doing this, why do we combine the three sensors, is kind of motivated by this study conducted by another PhD students in our group. She looked at sort of the distribution of clean, cloud-free clean observation spatially and temporally in sort of in the tropical regions. And what we notice is in some region, there just isn't enough optical data. For example, as some of you might already know, in sort of the coastal West Africa, it's very cloudy, so there isn't a lot of optical data. So what we want to do here is see if we can combine just different sensors so we can sort of increase the data density, and that would allow us to detect change faster. So we can find the most recent changes. And that's the reason why we're doing this, by combining these sensors. And sometimes there are some kind of disturbance in the forested area that is missed by the optical sensor, but shows up in the SAR sensor. So by combining these, we're also combining the capability, the detection capability of the three sensors, so to increase our chance of capturing some of the changes. So a little bit sort of into the technical part, how the algorithm works. Basically, I fit the time series model using 3 years of data before when we want to monitor. So for example, if you want to monitor the most recent changes in 2024, then I will use the 3 years before that. So 2021, 2022, 2023, 3 years of data to train the model to sort of figure out how the time series should look like if there's no change. And then I use that model to check the most recent observation in the monitoring period, for example, 2024, the most recent changes, right? So if I see that the actual observation starts to sort of deviate away from the model fitting from what it should look like if there's no change, then I say the model will say that, oh, okay, maybe a change has happened. And if we see sort of that change signal multiple times, and that's how we sort of confirm, okay, something happened, there's a change. So that's how it works. And then what we do is this training, this time series model is applied on each sensor separately. The reason for that is the optical data and the SAR data and the radar data are measuring very different things. So they have very different signal. So we have to fit the training and the time series model separately, but we do combine the change detection later. So what we do is we sort of group these observations into change and no change, and then we can combine these because that's then the same across all sensors when you sort of convert that to change and no change. So what I show here is the time series model fitted separately. On top, we have Landsat. In the middle, we have Sentinel-2. In the third row, we have Sentinel-1. And then in the bottom, what I show is the combined time series when you combine Landsat, Sentinel-2, and Sentinel-1. And as you can see, the density of data is much better. And so we have more data. It makes it easy to find consecutive observation to confirm the change. So if we just use Landsat, we find this deforestation late here where the pink arrow is pointing. But if we combine data from all three sensors, we can find the change much earlier. So that's kind of the reason for combining these different sensors. Okay, so I developed this algorithm. I tested it out in the Amazon, and we did sort of a formal accuracy assessment. And we found that basically, if you combine three, the performance of the algorithm is a lot better than using the individual sensors or the combination of two sensors. So when you combine three, you detect more change, and so you also detect these change much faster than using individual sensors. And that was tested in the Amazon. After that, after the testing in a few selected areas, basically I scaled the algorithm up with the help from Google. So they were very nice to grant me some free resource to save the results and to do the computing. So I was able to scale this up, and I created sort of the pan-tropical forest disturbance map for near real-time monitoring. So I have that map for 2023 and also for 2024. And also for the 2024 map, it's been continuously updated. So when we have more data, for example, next month, I'm going to rerun it and include the most recent data to update the map. So if you're interested after this training, you can check out my pan-tropical forest, near real-time forest disturbance map later. And my map covers the Amazon, West Africa, Central Africa, and Southeast Asia, basically all of the tropical areas. So today I'm going to show you a little bit how you can run it. So you can sort of adapt it and run the algorithm, which is called FNRT, in your own region. So there is a little bit of disclosure. So the algorithm was originally developed to monitor tropical forest disturbance. So I'm focusing on forested area. I also focused on sort of dense forest areas, tropical forest, the rainforest, the wet places. The focus of this training was dryland monitoring. So there is a little bit tuning or adapting that we may need to do to adapt it to your area. But that can be done. Also, I think I'm also curious on how this algorithm works in your area of interest. So before this training, Glory sent me a area of interest, which is basically the northern part of Ghana. So I have already run this algorithm for that part of the area, and I will show you some results today. I think I've looked at it a little bit. Some changes that we found are good. Some of them might be noise or not things that you expected, which is great. So I'm also glad to learn these. But if you want to apply it somewhere else in West Africa region, that's sort of what this training is about to show you how it runs. So the code to run things or run FNRT or the code to run also Luofan stuff is available on the Google Earth Engine. I created a repository called Severe under my username, which is Tang. So the link is posted here. You should be able to add this repository to your Google Earth Engine account by clicking that link. If that doesn't work, just email me your username or your email address that you use for Google Earth Engine. I can manually add you to the repository so you will have access to the whole thing. So for my part, for FNRT, there's basically three files that you need to pay attention to. There's the parameter file, there's the script that actually runs FNRT, and then there's also the script that will take you to a tool that allows you to visualize the results, the map, basically. So I will, for the next 20 minutes, I will walk you through this process, and then we can spend a little bit time. Then I will give it to Luofan for him to cover his stuff, and then we'll come back, and then you can spend a little bit of time using the visualization tool to look at the results that I already have for Northern Ghana, and then we can have a little bit of discussion on that, and I can answer your question if you have any. So to run FNRT, first you have to create a place to save everything, to save your results. So the data structure of FNRT is actually quite simple. You have to create a folder just to save all of the results. So one folder to save everything. You can call it anything. It's usually in your Google Earth Engine assets. So you create a new folder. Within the folder, you have to create three different image collections. You have to have a training image collection. You have to have a cache, CACHE image collection, and also a alerts image collection. So the training image collection saves all the training files. The cache saves all the monitoring results, and then the alerts will save the final maps, basically. So they have to be image collections, so not feature collections, not folders, just image collections. So do be aware of that. So this is sort of what it looks like. I know I also have an area of interest, an area in there that's specific for the region that Glory sent me. But to run FNRT in any region, that three image collections is all you need in that folder. Okay, so the first thing is there is a parameter file. This file contains everything you can set and everything you can tune or change before you run the model. So I'll show you what it looks like. Let me go to my browser. So here is Google Earth Engine. Everybody should be quite familiar with this JavaScript interface. on the left side, you can see all my scripts, and then there's the SERVIR repository. I will share this whole repository with you. Within there, there's a folder called Workshop 2024, and this is specifically for this workshop. In there, there's our two folders. The neural time stuff is what I'm presenting now, and then the multi-sensor fusion is what River or Luofan is going to present in about 15 minutes. So within my folder, neural time, there are three files. The first one we look at is the parameter file. So in there is all of the parameters that you can set. And if you scroll through it, there are a lot of things. It might feel a little bit overwhelming, but most of these you won't have to change. It's kind of how you process the data of each sensor. So it's not you most likely won't have to change any of those. Some things that you might want to pay attention to here, there's the forest mask. So I do use a forest mask to filter out areas that I am not interested in. Usually I use the forest class from the ESA 2022 World Cover Map for tropical forest areas. But because today we're looking at sort of more the dryland area, so I'm actually including not just forested area, but also shrubland, savanna, and agriculture areas. But if your interest is in tropical forest, you could change that forest mask to just looking at forest areas. You can also use Hansen's map or any forest map. Or if you have a better forest map for this region specifically, you can also use that. I also use a gridding system. The gridding system allows me to process or to run an area with using tiles. So sometimes your study area is very big, so you can't run the whole area at once or using one job on the Google Earth Engine because there's a limit in the memory and the computing power with each job. So we use a gridding system so we can cut the study areas into very small pieces when we actually run the thing. So the grid was designed for another NASA project called GLANCE. And here, as you notice, I'm loading the tile, the grid for Africa. So you see the AF here, which stands for Africa. Now, I would imagine most of you is going to try things in Africa, so you don't have to change this part. But just in case, if you are doing things in another continent, you can change that two letters into different continents too. So for example, if you want to run South America, you just change the AF to SA, and then you will be loading the tiles for South America. So another thing here in the parameter files that you might want to change is the area. Here, my study area in this parameter file as an example is this Workshop 2024 area, which is the area that Glory sent me, Northern Ghana. But if you're running things in a different area, you want to change that to your study area. This working directory is where you want to save your results. So remember, I mentioned the data structure of FNRTs is you have to create a folder and then 3 image collections within that folder. So here, WD, which means working directory, you have to change this to the folder that you created. So that's kind of about the only thing you might need to change. If you want the results in a different projection, you can change it here under projection. And other thing is the time period that you're looking at. So for demonstration of the algorithm today, I'm using 2023 for the demonstration. So I'm trying to detect all of the changes in 2023. So my training period is the 3 years before 2023. So as you can see here, my training period starts in January 1st, 2020, and then all throughout the last day in 2022. So the 3 years before the monitoring period is my training period. Now looking at the monitoring period, I'm looking at 2003, but I usually like to leave 2 or 3 months before 2003, before my monitoring period. So sort of to give the algorithm a little bit buffer zone. So that the reason to include that a few months of buffer zone is we want to detect all of the changes in 2023. And there might be some very early changes in 2003 in January that might be missed by the algorithm if you actually started right on 2003. So I usually sort of start a little bit, a few months early to give the algorithm a little bit of flexibility there so it can actually capture all of the changes, even the most early ones in 2003. So for this part, if you're looking at a different year, for example, if you want to look at 2024, you just have to change the dates accordingly. So you would have to change the monitoring date 1 year later, and then also change the training period as well. Moving down, there's sort of the parameters for different sensors, as you can see here. Most of these are just how you pre-process the sensors, so you don't most likely won't have to change any of those. Here, the only thing you might want to pay attention to is the Z threshold here. This thing sort of controls how sensitive the algorithm is. So if you want the algorithm to be more sensitive, basically detect more change, but also more likely to have false changes, false positives, then you will change the Z threshold to a lower value. If you change the Z threshold to a higher value, the algorithm will be more conservative. So it will detect less change, but it also have less commission error, which also means that the change that the algorithm detect is more likely to be real changes. So these are kind of the only thing you need to pay attention to. The rest of the stuff, there is the flexibility to change and tune a lot of the parameters. But for most part, you won't need to change any of those. If you're really interested in sort of learning the full capacity of the algorithm, feel free to read the paper or reach out to me, and then we can have a more thorough conversation on this. Okay, let me get back to my presentation. So that's the parameter file. As I mentioned, notable things that you might need to modify: the study area, the working directory where you save the data, the training and monitoring period, and sort of the Z threshold, which controls the sensitivity of the change detection. You can also change what sensor you want to use. So sometimes maybe you just want to use the optical sensor. You want to disable the sender 1, or you want to disable lens set, or you want to disable sender 2 and only use lens set. That's achievable. You just changed which sensor you want to use, and I'll show you how to do that. So the second file is the.
Jianxin, I'm sorry, I need to jump in. There's a question here. Will there be need to also change the buckets?
Sorry, what was that?
Will there be need to change the buckets also? You mentioned in what you showed us the scripts, there is a point where you mentioned the bucket, FNRT Africa. That's the name of the bucket. Will it need to be changed? In the question.
Okay, yeah, that's a good question. So there are two options to save the results on Earth Engine. Usually we save everything as a cloud asset here in the assets. In that case, you don't need to change the bucket. And also you don't need to change here. I'm showing the cloud option is false, meaning we're saving the results as a regular Google Earth Engine asset. We're not using the Google Cloud storage. So when you're processing a very large area, sometimes you don't have enough space to save in the regular Google Earth Engine assets. If that happens, you could also save the results in a regular Google Cloud, which you have to pay for. But that option exists with FNRT. So what you do there is then you will have to change this cloud option to true, and you have to change the bucket to the name of your bucket. That's only if you want to save the results on Google Cloud instead of the regular Google Earth Engine assets. That usually won't happen. I think most of you still work with just the Google Earth Engine assets. But if you do need to save everything on Google Cloud, so you have access to more storage, reach out to me and I can give you more details on that. When I did my pantropical stuff, which when I was covering a very large region, I did utilize the Google Cloud option. But for most cases, if you're looking at a country, usually you're fine with just the Google Earth Engine assets. Okay, I hope that answered your question. I'm gonna move on. So to run FNRT, basically I have created this second script here, which is just called FNRT. This is all you need to actually run it. So if you look at this code, it's actually very simple. It's only have a few lines of code. And the first part is basically I'm loading libraries from other script, and that's sort of from my main FNRT algorithm. So you don't have to pay attention to that. So a few things here is what you need to change. So if you have a different study area, change the area to your new study area. So there are two options. You can go to the parameter file and change it in there and save the parameter file. You can also change it here in the main script, FNRT script. So there's two options. Sometimes, I change things frequently. I don't want to go back to the parameter file, change it there. So you can also change it here. So as you notice in line 21 here, you can change the area that you want to monitor. In the second line, you can change the working directory is where you want to save it. And then in the next two lines, you can change the training period. Now at line 25, this is the line of code that you actually run the training. So I have commented out this line here because this is the first step. So if you want to run this, basically you uncomment this line and then you run this script here. You click run, and then it will start thinking and it will start trying to run it, right? So what the algorithm will do in this case is it will generate tasks here on the right-hand side to do the training. So the training is the first step you have to do. So it takes a while. You can see it's thinking now. It's figuring out a few things. It's trying to load the data that you need. It's also trying to figure out how many tiles it needs to cover your study area. So you might have to wait a few minutes for Google Earth Engine to figure those things out. What data to load, which tile to run. Once it figures everything out, what Earth Engine will do is it will generate those tasks for you. But you do have to run the task to finish the process. The task will be run in the background, and then it will generate the training results, and it will be saved in the working directory in the training image collection. So I'm going to let it run, and I'm going to sort of just go through the presentation here. So my the thing shifted a little bit, I think, because different version of the presentation. So this is on the right-hand side here. If you can see my mouth, this is what the tasks look like. The task, what you see here is H019, V023. That tells you which tile it is running. And then the second part of it tells you which sensor. So LST is Landsat, S2 is Sentinel-2, S1 is Sentinel-1. And then which year. So this is the last year of the training. So I'm monitoring 2023. So the last year of my training in 2022. And then the T is for training. For Sentinel-1, because there's different orbit passes, so you might have different tasks to cover that different orbits. So what you need to do is run these tasks for your study area if you're doing it in a different area. And as you can see, it might take anything between 10 to 40 minutes to run the training, depending on the sensors that you're doing and depending on the resolution of the sensor. So I'm not going to run it now. I have, as I mentioned, I have already run it for our study area for Northern Ghana. So as you can see, it's giving me this warning that this tile, this results already exists. So if you're doing things in Northern Ghana, it will tell you the same thing. The results already exist, so you don't have to do it. But if you're running it in a different region, or if you have changed the working directory to your own folder, then new tasks should be generated, and then you should be able to run it to actually run the training. So the second step, once you finish the training, you have to wait till all the job is done, all the tasks are done. Once the training is finished, you can move on to the monitoring. So you don't have to retrain it every time you remonitor, you do the monitoring. The training, usually one training for 3 years is good for 1 to 2 years of monitoring. So what I do is I do the training and then I usually do the monitoring. And then maybe 1 or 2 years later, I think it's time to retrain it. And then I will update the training period and then I redo the training. That's what I do. For the monitoring, let me go back to the code. It's actually quite straightforward too. So there's a few things you can set. So as you can see here in line 28 through 30 of the code, this is where you choose which sensor you want to use. So I'm enabling everything. So I want to use everything, Landsat, Sentinel-2, and Sentinel-1. If you don't want to use any of those, just change it to false. And for the monitoring period, as you can see here, I'm setting it to 2022 October to 2023 April. So the reason I didn't do the full year of 2003 is I want to demonstrate to you that you can separate the monitoring period. You don't have to do the full period at once. You can do half the year, and then you can do the other half of the year later. The algorithm will be able to read from the existing results, so it can sort of do the continuous monitoring. And the nice thing about this feature is if you're actually doing things in real time, for example, you're monitoring changes in 2024, sometimes what happens is when you do things in real time is you have to pause and have to resume it later when more data comes in. For example, today I can set the monitoring period from up to June the 30th, which is yesterday in 2024, and I can run the monitoring, right? That's all the data we have, right? That's yesterday. That's literally yesterday. That's all of the data we have. That's near real time. So I do the monitoring, I look at the results, and I'm happy with it. Now, a few months later, we have more data comes in, right? 6 months later, and we're at the end of 2024. So now we have 6 months more of data. Now you can rerun it. So you just change the monitoring period from July 1st to the end of 2024, and you can rerun the algorithm. So what's nice about FNRT is with the cache saved, or with the results from the last monitoring saved there, it can pick up from where you left off. So it will be able to read from your previous results and sort of continue the monitoring. That's it. And it's quite handy when you're actually monitoring things in real time. Yes, Glory, is there a question?
No, not at this time.
Oh, okay. So with that is when you do that, you'll see in the console, it will print out something that says successfully read the cache. So you know it did read the cache. So you only have to make sure the new monitoring period is follows. It's right after the old monitoring period. So it will be able to read the cache. So to do the running, it's the same thing. It's a step 2 monitoring. Once you finish the training, you want to run the monitoring, you just uncomment this line and you click run. It will then generate the task for the monitoring and you run the task. Usually it takes 30 minutes to run each tile if you give it like about 6 months of data. And then it might take another 30 minutes to run if you update it with another 6 months of data. So that's step 2. The last step is what we call filtering. What the filtering does is it filters out small changes. So basically what it does is in remote sensing, sometimes what we get is this kind of salt and pepper effect where you have these noise in the results and you don't want it. And you just want to look at changes that is larger than a certain threshold, a certain size. Usually what we look at here is changes that is larger than 8 Landsat pixels. So that's what the filtering does. It's a spatial filtering. It will throw out all of the noises that's smaller than 8 Landsat pixels and only keep the real changes. So what you do with the code here is at line 37, you uncomment this line and you run the filtering. So you have to let the monitoring jobs finish first, and then you run the script here to generate the filtering task. And then you run the task. The filtering process is much faster. Usually only takes about 10 minutes to run each tile. Oh, by the way, each tile is about 100 kilometers by 100 kilometers. So it covers a fairly large area. So once all of the job is done, you officially completed all the steps of FNRT, and then you're ready to visualize the results. So that we move on to sort of the last script, which is the visualization tool. The visualization tool is the visualize script. Looks like this, only a few lines. So you run it, and this is what the user interface looks like. You have a map area on the top where you look at the maps. You have a time series plotting area here, which you can look at time series of individual pixels. You also have a control panel here, and you have a few tools, and I'll show you how to use it. So by default, it will load all of the changes, and you can look at sort of our study area is the northern region of Ghana. This is our study area. Let me zoom into a few changes that we detected. Sorry, my internet is a little bit slow. Let's see if it will cooperate. So we detect quite a few changes. I have to tell you, some of these are real. Some of these might be noises, false positives. I haven't really spent a lot of time trying to tune it in this region. As I mentioned, it was originally designed for tropical forest. But it did detect some real changes in this region. I can tell you that. Some of these, you can see the pattern. They look real. These are real disturbances in this region. So this is how you sort of visualize the results. You also have a few tools you can use to look at individual pixels. For example, let me zoom in to this patch of changes over here. The color indicates when the change happened. And this is in 2023. The orange color is most likely in the middle of the year. So look at the control panel here. You have a few tools you can use. There's the CCD button, lets you visualize the training and some of the detection of individual sensors. So here I'm choosing Landsat. You can choose Sentinel-2. You can also choose Sentinel-1. So I'm choosing Landsat. So you click the CCD tool to activate the tool. Now it's activated. So it no longer says CCD here. It says cancel, which is if you click again, it will cancel the tool. So once the tool is activated, you can then click anywhere in the map. So let's say I want to check this pixel. I want to see what the time series looks like. So I just click there. You can see a blue box is added there, right? So that's sort of telling you where you clicked basically. So you have to wait a few seconds. The program is thinking, it's trying to load. Here we have. So here's the time series for that pixel I clicked. You can see for the 3 years of training, from 2020 to 2003, we have a regular pattern, and then you can see the time series model, right? So we use the same model to predict what things looks like in 2023, but you notice that the actual data, which is the red points, looks very different from the model. So that's how the algorithm know a change has happened, and then that's where the change is detected. So that's how you check individual pixel. Another nice thing about this tool is, so every dot here, every blue dot, every red dot is one image, is a data point, right? So you can click on any of the point, and then it will load that image for you. So you can actually visually look at that image. So this is Landsat. So you're looking at that particular Landsat image collected on June the 18th. So that allows you to sort of actually look at the individual images. So you can click on any of the dot, it will load that image for you. So you can actually look at the image before and after the change. So that's sort of the CCD tool. The NRT tool also lets you look at sort of the change detection results. So that's the near real-time change detection results, and you can do it with different sensors. So for the NRT results, it can load multiple sensors at the same time. So here I'm checking all three, Landsat, Sentinel-2, and Sentinel-1, and I can click the same spot. It's going to try to load that for that particular pixels. Now, it might take a few minutes to load that. I'm not going to wait. I already have something loaded in my presentation. So I'm just going to go through the slides here, and then we can come back later. So this is also a pixel in northern Ghana, and you can see the Landsat training, and then the change happened in 2003. And then in the bottom, there is a Sentinel-2 near real time plot. So it's showing you the change score, the higher change score indicating that it's more likely a change has happened. So you can see the change score increased significantly in 2003, and that's when the actual change happened. So this is where it was located. It's actually near the border of Ghana and Burkina Faso. It's sort of north of Tamale, and that's where I think it's a big mining event. So here I'm showing you the Landsat images. On the left, it's the Landsat image before the change. On the right, it's the Landsat image after the change. I think it's a mining event. And here is a near real time plot, which is the change detection results from different sensors. Landsat, Sentinel-2, and Sentinel-1. You can see the change was detected around June with the individual sensors. But if I combine all three sensors, the change was detected much earlier in May. Okay, so that's sort of all I'm presenting for my part. This is my last slide. I'm showing you I want to show you sort of a few links to sort of the other things I mentioned. There's a GitHub link to the full FNRT results. The thing I presented in my Severe hub is sort of a simplified version, easier to use. But if you're interested, if you want to use the full thing, here's the link where you go to. And then I also have a few maps already created for the tropical region for 2023 and 2024. So here are a few apps where you can use to visualize the results. I have it for the whole tropical area, different regions. I have it for just West Africa. I also have it for just Ghana, created with the request from Bash. So there are links that you can look at. So with that, I'm going to pass it to River so he can present sort of the second part of this thing. River, do you want to share your screen?
Okay, let me try. Share my screen. Share. Let me see my screen now.
Yes.
Okay. So, hi everyone. Today I'm presenting 3 parts. The first part is introduction to time series change, which Xiaojing already covered some of that. The second part would be my work in southern region. I'm doing land use and land cover change mapping in southern and West Africa, mostly tropical forests in Ghana. And the third part, I did some study in Savannah region using the same method. Now move to the next slide. This slide is about Tang series model. It's called CDC, which Xiaojing already said. So when we have millions image available, we can use all of them. Like here, for this pixel, we use all the images and we use all the observations and we plot that in Tang series so we can detect a change. Now from using equation, how did that work? Like we have all the observations and then what if we fit that to a linear model, like the first two terms, with T as time and the output as the spectral signal? If we fit a time series with a linear model, we can see if the time series is increasing or decreasing. But still, we can see it's quite noisy because there is a seasonality. So the root mean square will be very high if we just use a linear model. So we add a harmonic coefficient to that. So we can also fit seasonality into our model. Then when we do a classification, what we do is we use these A, B, and C, all those coefficients as inputs for classification instead of the spectral signal of individual image. Here is how we detect a change. So if a new pixel is fall within 3 times root mean square, we say that is a valid observation. There isn't a change. But if a change is outside of 3 times root mean square, we say if 3 pixels or 5 pixels in a row says there is a change, then we fit a new model. Here is a very nice example previously made by Zhu, who wrote this paper. So this is an online model, meaning if there is we fit a model first, and then we update the model when there is a new observations comes in. Now we see there is a new observations adding up into the figure, and those cloudy and not clear observations, we don't use those pixels. They are in the show. They show in the bottom. Now we keep updating this model when there is a new image available. It should be very useful, so we don't have to rerun this whole thing every time we got a new image. Now we will watch this until we detect the first change. So, and here we show 3 different spectral bands. Sorry, we show that 3 different pixels. They're all in square band, I think. It goes on and on. Now we find a potential change here, but we need 3 or 5 potential change to mark there is indeed a change. Now, as here we can see, because there's 3 pixels already marked as change, maybe 5. So we have to build a new model, and that's a change detected. As the model moves on, the other pixel was still no change, but the pixel A, we find a change. And if we look at here, it's apparently deforested. Now move to my part. I'm using an index called NDFI, which is very sensitive to forest disturbance, especially partial forest loss. This is very useful in dense forest cover. And I also combine Sentinel-1. The Sentinel-1 I'm using is pre-processed in Google Earth Engine. You can find this paper. It's industry standard how to process Sentinel-1, which might be not perfect, but we can simply just use this in Google Earth Engine. Then I calculate GLCM texture at 10 meter resolution. You might argue Sentinel-1 is not really 10 meter, but that's what I did. And then I resample everything to 30 meter to match the resolution with DenseSet. Now at this figure, I show an example. I show the NDFI Tang series in the bottom and the Sentinel-1 VH band on the top. We can see the data density is very sparse, especially before Landsat 8. And data density is much better in recent years. We might also notice there are 2 changes. The first change in 2016, we found some decrease in NDFI, and the second change in 2021, we saw a great decrease in NDFI. After the first change, the canopy seems to recover. Now, if we look at the high resolution image, we see tree cover like this is like this in 2013, in 2015. It's still nicely a tree cover. In 17, we see some big trees is missing from site, but it might already recovered from the logging event or whatever happened. In 2021, it's a big change. All the trees are gone. So then if we look at Sentinel-1 data, we can see a pattern. Like in 2021, there is a big change, a very little change in 2016. And the data is very noisy. The data density is much higher compared to Landsat. Now, if we fit CTDC model to that, we might find 2 changes as we just showed. And that separates the whole Tang series into 3 segments. And each segment is considered as stable land cover. It depends on how we define stable. For the first segment, we say it's stable forest cover. In the second segment, we see there is a recovery here, but still it's considered as stable. And then there is the third segment. We use all those coefficients for classification, and we can also calculate something called synthetic image. Because if we look at the equation here, the input is time and the output is a spectral signal. So for example, if we want to know the spectral signal in 2017, like we don't use the real observation, we can use the model here. So we use the time and we get output from here instead of the real observation. That's what we call a synthetic image. Then now we add Sentinel-1 to the image. We see the segment also separates Sentinel-1 into 3 segments. Like the first one, we match those blue points into the first segment. And the second one, for the second segment, we see those orange points from Sentinel-1, we match that. And the third third segment are showing green points. Those gray points, we are not using those points because they are in between segments. That means there is a big change and the land cover is changing very quickly. So we are not using those data. Then after we match Sentinel-1 Tang series with the start date and the end date from CTD segment, we can calculate something like median value. We calculate median value for all those points, and we use that together with the first segment. So we can do some classification or anything else. We can also calculate GLCM texture for each segment and also calculate the median value. And then I'm showing more examples. Like here is a logging activity, and then we see 2 changes. And Sentinel-1 is also shown on the top panel. Other examples like another logging activities, urbanization. This is the example I just showed. And then there's mining activities. This is quite interesting because before the mining actually happened in 2022, there were multiple logging ahead of time. And then there is a forest change to rubber, and there is a stable cocoa. I show this example because we see Sentinel-1 only covers parts of the time period. It doesn't cover from 2000 to 2022. It's the same with any other radar data. It covers like very limited time period, but we can see the whole segment is benefits from this like 6 or 7 years Sentinel-1 data, as long as we consider this segment as stable land cover. Also, we can see here, the first segment, we only have 1 or 2 years of Sentinel-1 data available, but we can still use that for classification if we consider the first segment as stable land cover. Now, if we apply that into a land use cover study, land cover change study, here's my study area. This covers the southern Ghana and southern Ivory Coast, where the optical data is really scarce. As Xiaojing already also showed, the southern region, especially here, There's very little data and very difficult to run the CCDC Tang series model over regions like this. So we figure if we can run Tang series in here, then it might be easier to run the same model somewhere else. And these regions are also very complicated because it's dominated by smallholders, and the land use and land history is also very complicated. Here is a workflow. First, we got some samples, random sample for change detection. Mostly, we got this sample and we label those samples by looking at the Tang series. We label if there is a change or not manually. Then we change the CCDC parameters so we can detect as many changes as possible. Is somebody raising hands? If there is a question, please just let me know. And if not, I'm gonna keep going. So after we tune the parameters, we found out that the omission rate of change detection reduced from 50% to 8%. That also means we are detecting more false positive. These are some minor changes. They might not actually be land cover change, but we still found that. So we have to filter those out. Then we can combine multiple radar data with all the segments we have to, like, we use parser because parser 1 goes back to 2007. With parser data available, 75 of the city segments in 2000, they have at least one kind of radar data. After 2008, because of the parser 1 was included, 100% of the pixel. That means every pixel in the region has parser data available. So if you are doing land cover change study like after 2008, this is perfect. But still, in early 2000, there are 1/4 of the pixels we might need to pay attention to because they don't have any radar data. Now, here is the land cover map results in 2021. And here's 3 rooming examples. Like this region, we found 2 rubber patches and the small rubber patches here. And we found some oil palm in the middle. And like we can room in here. It's very complicated. And we classify some of the cocoa region here. Then the second example is a mining region. We found some grassland, cropland, cocoa region on the left, and there is a huge mining site in the middle. And there is some tree covers in the middle of mining site. On the right side, we see a very complicated region where we have oil palm, rubber, and cropland everywhere. Then we are also working on some other things like, can we map oil palm or rubber replanting? And when did those oil palm was replanted? We're also trying to detect mining. And we are trying to improve those in the future. And the third part, we are doing a case study, as Glory showed the study region. So here we try to figure out if the Sentinel-1 data can help in Savannah region. We show some examples of Sentinel-1 data in agroforestry field. Here's the link to the scribe. It's also in Xiaojing's repository he just showed. Now, I ran the results. Here is the Sentinel-1 VVVH and VVVH ratio composite as shows in RGB channel. On the right side is the RGB synthetic image from CCDC. They are both in 2021. Now, before we explain what this means, we show some rooming example. The first example here, we see there is a patch of bare ground in the middle, and there are plenty of tree covers surrounding there. I hear some echo sound. I'm not sure if anybody heard that. Okay. So this patch of bare ground on Sentinel-1, we see it in purple color. I show you 2 examples, 2 pixels here. The first pixel in background, we see much higher ratio. And the second pixel here, it's tree cover, which we see lower VVVH ratio. And if we look at the see this is synthetic image, this shows as background, which is in bright color compared to the surrounding region. If we zoom out a little bit, it's very clear. This patch in purple here is just cleared and clean. It's a background patch. And the second patch here is the same. And we can see this road here is also in purple color. If we look at this patch here, it's very dense tree cover. It shows in bright yellow as compared to the surrounding region. On the right side, I'm showing the GLCM texture, which shows how one pixel is related to the surrounding region. We see here, this patch shows VH correlation, and the second one is contrast. The third one is variance. It's very interesting because this patch of dense tree canopy, it shows up in contrast, and this patch background here, it shows up in correlation. We think the GLCM texture might be useful for different kind of land cover. It really depends on what kind of things we are trying to find. The second example, it's a very complicated agroforestry field. I'm not sure if you will define this field as agroforestry. So here we found this patch is clean cropland, and this patch on the top and this patch on the bottom. There are some trees in the middle of the field. Now, if we look at Sentinel-1, this patch shows in bright purple color, where the other two patches it's darker, and this strip of tree covers it's in bright yellow. It also shows the VVVH and VVH ratio here for these 3 pixels. These 3 pixels, they are dense tree canopy for the first one, the sparse canopy for the second one, and this is a very clean cropland. And I show the value here. For the cropland, the VVVH ratio is much higher, as we said, and the second and third one. For the second one, the sparse canopy, it shows much lower ratio, and the third one, it's even, for the dense canopy, the ratio is even lower. Now, if we zoom out a little bit, what's very interesting is this patch here. It's a shrubland, and also you may call that sparse tree cover, and it's very different compared to this strip here. This is dense tree cover, and on this synthetic image, the difference is not quite obvious. If we look at the GMCL texture, this patch here is very different from this patch here. Also, we can see this clear cropland here is also marked out in dark color. And if we look at ASM, this patch of cleared cropland is very bright. So we do think it's potentially useful for differentiate different tree cover level, even in savanna region. Here's the third example. It's also very complicated area. We see a cleared cropland in here, and we see the cropland with some tree covers on the right side. All 3 examples are shown in the scribe. Now, if we look at the map, look at the entire region here, we might conclude this region here, it's more likely to be dense tree canopy or shrubland. And the second region in orange, this region, it might be very dense cropland, intensive agricultural activities. The other 2 regions, they might be more like a mix of agricultural land and some trees in the middle of the field. And here are some takeaways. We think multiple sensor fusion can take advantage of each sensor. Like Landsat covers very long time period, but Sentinel-1 doesn't affected by cloud cover that much, and the data density is very high. It might help to map detailed land cover classes, we separate different tree species, different kind of plantations, and potentially it might differentiate different tree cover levels. However, we might also say there are some disadvantages because the data volume is really high when you use multiple sensors, and we need to try to resolve the differences between sensors. Like the spatial resolution is different, the temporal coverage. How do we resolve these differences? And now I want to share this here. Can you see that? So if we go to Xiaojing's repository, let me find that workshop here. Can you see my screen?
I think you're still sharing the PowerPoint.
Okay, let's see how can I share this screen here. So if we look at Xiaojing's repository here, we might find this under this folder, there is a multiple sensor fusion. And if we click here, we see this scribe. Here are 3 examples. We can just run this, simply click run and move to the study region, which is in northern Ghana. We see these 3 examples I just showed, like the first example here is the patch I just showed. If we open the layers here, the bottom one is the VVVH and VVVH ratio composite from Sentinel-1. You can move this here to change the transparent value of this layer. You can change that to 50%, for example. So you can both look at the Sentinel-1 results and look at the background image. Right. So we can see this patch is cleared background. And you can also open all the GLCM texture layers and look at any layers you want to see. Here is the 2 synthetic images. One is from the CADC Global Run, which is available. I'm not sure if it's publicly available. I think maybe you can reach out and we can try to see if we can make that available for you. Because using the global run, you don't have to run CADC for yourself. But here's the problem with the global run. If we look at the southern region, let it load for a while. Sorry, I just ran this for the northern region, I forgot. So anyway, the southern region, you might see some areas there isn't any data available from the global run. Feel free to look at the map and check out the regions you are interested in. But for here, I only shows the results within the study region. I think at this time point, I'm gonna stop sharing, and so you can look at maybe Xiaojing's near real-time results, or describe if you want to look at the data fusion from multiple dense sensors based on my results. And then we can, if you have any questions, or we can discuss anything you want to talk about. Thanks.
Thank you very much. Okay, Julius has had his hand up for a while. Can you please add that question? Julius, please.
Oh, sorry about that. That was probably clumsy of me. Probably clicked it by mistake. Sorry.
Okay, great.
I always do that, sorry.
Okay, now Mohammed has his hand up. Mohammed, what a question.
Thank you for giving me the floor. So my question is about the CCDC algorithm. So about the curve which is describing the evolution of which is able to detect a change in the specific area. What I want to know is about, firstly, it's about the dimension of the area, like which which number of meter square that change is. So the curve is located in which dimension of the area. And the second one is about the time. So which time, like if the change happened like 2 days before or 5 days before, we need to be able to detect that. So thank you.
Right. Thank you, Mohammed. I think for the first question, I will rather ask Bashara to answer him, because asking about the extent of the study area used for this demonstration. So Bashara, can you answer that if you're there? Bashara, are you there?
Yes, Laurie, I'm here. Yeah.
Okay. You heard,
So
you got
with
this
that
question.
part of the area, can you repeat it again? I got it, but you can still repeat the question.
He was asking, how large is your study area?
Oh, that's big. The study area, I can't readily calculate it now, but what I can say is that is over. Just give me 1 second, please. Let me just be sure.
So the area that was sent to us is basically the northern half of Ghana.
Mhm.
That's the area I used to demonstrate the FNRT algorithm today. But I also have results available for basically all tropical areas. And for the CCDC part, there is a global CCDC run available, so it's global, just using optical data. And the change detection was done. You could plug in your training data for classification of the results. And I think we have code ready to do that. You just need to provide the training data. We have already run the change detection. We could also run a specific region for you to include some of the Sentinel-1 results, or we can let you run any region of interest as well.
So please, I think I can reformulate my question. So my question is about the dimension of the area where you click. You said that when you click in any area, you want to have the curve describing the change related to that area or related to the click. So I'm asking the dimension of the click, the area located around the click.
Oh, okay. So yeah,
like
so in my demonstration, sorry, go ahead.
So I mean to like a radius, or is this in a radius of the click, or yes? So if it is the radius of the click, which is what is the dimension of the radius?
Okay. Yeah, if I understand your question correctly, when I sort of demonstrate a tool, I clicked one place and I show the time series and the changes, right? So in that demonstration, wherever I click, it will show the change detection results of that pixel. So it will be a 30 meter by 30 meter pixel for Landsat, 20 meter by 20 meter pixel for Sentinel-2 and Sentinel-1. So we're just showing the time series is just for one pixel. But in the example that I showed, where I zoom into a very specific change event, I think the size of that event is about, I would say, 300 meter by 300 meter, because that's like multiple pixels. But the time series plot is just where I click. That's only one pixel.
Okay, that's fine. It's clear now. So about the period, so if the change happened like 1 week ago, will the algorithm be able to detect that change?
Can you repeat the question?
About
My
the
internet is
time
cutting off a little.
About asking about the time interval for the algorithm to be able to detect the change. What is
Okay.
the time frequency? Yes.
Yes. So for the neural time algorithm, we detect change using 4 observations.
Yes.
And that will depend on the density of the observation. Obviously, if it's more cloudy, we get less optical observation, but we have steady Sentinel-1 observation. So I would say in this area, if you use Landsat Sentinel-2 and Sentinel-1 together, usually we can detect the change within a month of when the change happened. We just need 4 observations to confirm the change. And how long it takes to get that 4 observation kind of varies a little bit depending on which season and what area, but in general, 4 observations.
Okay, thank you.
So there was a question in the chat, how do we generate the training data? So training data can come in the form of points or polygon. Basically, you provide a shapefile or a feature collection on Earth Engine, and then it needs to have, if it's points, every point needs to have a class associated with it. If it's polygon, then every polygon needs to have a class associated with it. Savannah landscape is tricky. As you said, you had a lot of misclassification. We found it very helpful to include some of the SAR data that improved our classification in separating different kind of plantations. But we haven't really tested extensively in Savannah region. We're very interested in doing that. I think that will be beneficial. So on top of the optical Landsat CCDC, we add in the Sentinel-1 and ALOS pulsar metrics that River calculated and the textures, and try to rerun the classification with those. You might get better results.